Okay, continuing with Chapter 4, we've got a block of information on IP addressing to cover today, so let's get into it. The Internet Protocol datagram format has room, like all the layers headers do, for addresses. And we've worked our way down from the application layer where we use process IDs to the transport layer where we use port numbers, and now we're at the IP layer where we use IPv4 or IPv6 addressing. Those are the two versions of addressing that are prominent. And most of us as end users will use IPv4, at least for now. IPv6 has been around for a long time, but a whole variety of things have kept it from rapidly becoming the dominant standard, including some things that we'll look at today. So there's a few things going on in the network layer. The network layer is considered a collection of subroutines and blocks of code that usually run in the operating system so they get the speed that they need. And that's one of the things that's going on is the IP protocol. But there's some other things happening as well. One of them is ICMP, which you had a Wireshark lab on. And ICMP sits basically up above IP. It uses IP, so it generates messages and can send things out via IP. There's also ARP, which we haven't really talked about yet, and we'll get to a little bit later. That's a block that runs in there that we're not going to look at quite yet. And then there's routing protocols, which is the algorithm block of code that is constantly trying to figure out what the right forwarding table is for your router. In other words, it's trying to learn what other networks are accessible and how best to reach them over which of the links that it has. So for some of the core routers, it's a massive table. For some at the edge, perhaps it's a little bit simpler. But all these things are running and they interact with each other, so it's not just a single program or a single block of code, and there's even some other things that aren't really mentioned here. So let's take a look at the IP datagram format. There's a version number up front that tells you what version of IP you're running. For most of us, that's going to be 4. There's something that tells you the length of the header, and that's in multiples of bytes because there's not enough bits. So there's an interesting thing that goes on here. If you've got normally, let's say, an 8-bit number, and you can represent from 0 to 255 with it, or as we would say, 256 different values, and you don't have room for 8 bits, what you're basically going to do is still probably want to support a decent-sized range of data, but as you cut bits off, you're going to have to use the bits that remain to represent multiples of bytes at a time, so you can still reach the total. So for example, if I have all 8 bits, then I can have all 256 combinations of the numbers 0 through 255. But if I rob one of the bits, then it means that this 7 bits that's left doesn't get to use the 8. And so if the 7 bits are, whatever they might normally be, let's say they represent 124. That's the binary number that I've got here. Then 7 bits is basically going to be the 0 and the 1 bit for the 8th bit at a time. So each one of the 7-bit combinations, which is always going to end in a 0 here, since I don't get to specify it anymore, is going to represent 2 bytes. If I rob another bit, then it's going to have to represent 4 bytes. If I rob another bit, then each of the numbers is going to have to represent 8 bytes. So you'll have to make sure that the length that you need it to be is in multiples of 8 or 4 or 2 bytes, but you'll still be able to represent a big number. You're not going to be stuck with representing just like 2 to the 6th or 2 to the 5th or 2 to the 7th, something like that. So that's the scheme that we're using. And you'll find that in header length, we require that it be a multiple as well. You'll see that again when we get to fragment offset. So a little more on that later. Type of data, and then the maximum number of hops that a packet can be allowed to move itself across the internet before a router discards it, complaining that you've been hopping around too long. There's probably a loop somewhere in the path. So I'm going to send an error message back to your source and let them know what what's happened. Upper layer protocol would be usually TCP or UDP, and the overall length of the datagram, including the header, is in bytes. There's no truncation here. It can be the bytes you need, although interestingly, the datagram is always a multiple of bytes. It's always in 32, at least the header 32 bits, and you'll pad things. There's some there's a row in here. There's some fields used for when we have to divide a packet up because it's too big, and then how we put it back together. That's called fragmentation and reassembly, so we'll talk about that. And then there are some optional fields in here, things that you may need to set aside space to record some variables that you need recorded by a router, or perhaps other options that deal with the handling of the packet. And then, staring us right in the face here are the two 32-bit IP addresses, the source and the destination. So how big is this thing? This is significantly more complicated, say, than the UDP header that we looked at. It's kind of on par with the TCP header. So there's 20 bytes of TCP that are buried in the payload. And that's going to be the first part of our payload because this is at layer 3. And so everything we carry in our payload is all the layers above us. So there's going to be some here for layer 4, and there's going to be the rest here for the application layer, layer 5. So we know that we are stuck when it's with TCP with 20 bytes of overhead, and then IP requires a minimum of another 20 bytes of header, plus whatever optional you can do. So 40 bytes overall before you send any data at all. You remember the Telnet example where we were sending sequence numbers back and forth when we first learned about them with just one character per packet? That's an example of 40 bytes of overhead for 1 byte of data. So we don't want to flood the network with nothing but those kinds of packets because they're too expensive. Okay, one thing that can happen to an IP datagram as it's making its way through the internet is you can run into a router that doesn't have access to a network that can handle packets as big as you like. Every network designer, every network engineer specifies the minimum and maximum size of a packet on that type of technology. That's true for Wi-Fi and Ethernet and every other technology in between. And so sometimes if you've issued a packet that's a decent size to you, but somewhere along the journey it reaches a router that's running on a technology that can't handle it, the packet's going to have to be broken up. And we advertise how big a link can sustain using a variable called an MTU, maximum transfer size, maximum transmission unit is really what it stands for. And it's the largest possible layer 2 frame. So you back away from that a little bit for the header, for the frame, and then you're into IP, and it eventually works its way all the way up to TCP and perhaps the application. So you can ignore these things at the higher layers, but you do so at your peril because a good designer will be aware of the size. And so if you're doing a streaming radio app, for example, you won't want to knowingly send packets that are going to get fragmented because it adds delay to your packets. So we try to discover what the MTU is for each of the links along the way on a network using an MTU discovery process. But again, it's optional, and fragmentation sometimes does still help. So here's an example of a packet that's taking a certain path, and it arrives at a router that requires that it be broken into 3 smaller datagrams. Once a packet's been fragmented, it will not be reassembled except at the end host. And if you think about it for a while, you can convince yourself why there's no other possible way for that to efficiently work. Once you've fragmented frames, there's a reason why you let the host at the end deal with it. Now, once a frame is fragmented, each of these fragments are full-blown IP datagrams. They have a header, they have a body in it. The difference is what was the body, the payload that you were carrying, which included, as we just saw, maybe 20 bytes of TCP and then some application data. If this whole thing with the IP header on here is now too big for a path, what you're going to do is divide this up, let's say 3 pieces, 1, 2, and 3, 1, 2, and 3. You will probably suppress putting all of the optional fields here on all of the packets and put them on just maybe one of them. And so you will take this part and this part, and you will build a new datagram. And then you will take, switching colors here, you will take the same IP header again, and the second part this time, and you will build yourself another IP datagram with a smaller IP header perhaps, and part of the original payload. And then, for the last one, you'll take the IP header again, and the last part of the fragment, and build yourself a third one. So these are fully routable, independent IP datagrams. They don't stick together, and there's numbering in them to help you put things back together at the end. So the reassembly happens at the end. So here's an example, a 4,000 byte datagram, and we know it's a 4,000 byte datagram because the length field has 4,000 in it. So this is the entire datagram, including the header, right? So our maximum transmission unit for the network that we just arrived at is 1,500 bytes. So we have a problem. 4,000 bytes will not fit into a 1,500 byte network. So we're going to have to fragment it. So we can make each of these 1,500 bytes long until we finish the thing out. So why is this not 1,500, 1,500, which would get me to 3,000, and then 1,000? Why is this 1,500, 1,500, and 1040? Well, let's look why. My first datagram, I'm going to have some number of bytes in there, but I still have to have a 20 byte header. So I can only fit 480 bytes in here. And in the next one, I've got the same thing going on. I'm going to have another 20 byte header, so I can fit another 1,480 bytes out of the 1,500 for payload. If I add those up, I'm at 2960, and I need to reach 4,000, but really in a packet that's 4,000 bytes long, the payload is only 3980 because 20 bytes of this one was payload as well. And that's assuming all this is the minimum header, which we're doing to just kind of keep things simple. So 3980 minus 2960 means I only need to get another 1,020 in here, and I'm going to have to add a 20 byte header on top of it to make it complete, and presto, there's our 1040. I'm as impressed that I was able to do the math as you should be happy that it seems to be somewhat elegant. So I have my links in here, and do you remember the offset field that we had in the header? I'm going to back up and show it to you one more time. Hopefully it's not too far back here. It's right here. This is 16 bits long because it's half of 32, but 3 of the bits in here are flags, and so we only have 15, 14, 13 bytes left. This is one of those examples where I've robbed 3 bits, and so I only have 13 bits left, but I want to be able to represent a number that is between 0 and 256. So as long as you're willing to represent sort of hops along the way, this is 3 bits, 2 to the third equals 8. And so I'm only going to be able to do it every 8 bits, so it can be 0, 8, it can be 16 bits long, and so forth. And so you'll continue on this way. And as long as you make sure your packet that you're trying to represent, the fragment length, is a multiple of 8 in length, then 13 bits will do you fine. You can get away with it. So that's what's actually happened here, is we've indicated with this 13-bit field, which we call the offset, where in the grand scheme of things these chunks that we've built fit. So I had my original payload. I broke it into 3 parts. And remember our sequence number, the way sequence numbers worked in the fact that all throughout here we're kind of keeping track of bytes. This is byte 0 in this datagram, and this was byte 3980 in this datagram. And so if I'm going to start dividing things up and they're going to be full-blown datagrams again, I need to let the person who's going to reassemble this at the other end understand, here's a chunk. Okay, well, which chunk? Well, the first chunk. Well, what does that mean? Well, it starts at byte 0. Aha, okay, thank you. And how long is it? It's 1480 bytes long. All right, so when I receive that, I know where to put it. I'm going to put it starting at 0, and I will leave a blank space after it. And then I get another chunk. It's chunk number 3. Well, that tells me nothing. Well, it's actually the chunk that starts with byte. And do you remember we had 3980 here in the beginning, 1480 in each of these. So I've got 2 of these 1480 chunks here. So I add those together, and I'm going to get 20, let's see, 8 and 8 is 16, 4 and 8 is 9, 2960. So this is going to be, start at 2960 because I really started at 0 over here. So this went from 0 to 1479. This went from 1480 to 2959, and this goes from 2960 to 3980. And that's how the numbers work out. So I need to label this packet that it starts with this one, and I need to label this packet that it starts with 1480. So how am I going to do that? Well, I can only number in multiples of 8, so I divide the number by 8. So for this second one, 1480 is the starting point. Dividing it by 8 gets you 185. So this starts with the 0th octet, this starts with the 185th octet, and the last one starts with the 370th octet. Okay, so tons of stuff there on fragmentation. Let's talk about addressing. The hosts on the internet have 32-bit addresses, as we know. And what this diagram shows us is a network diagram, maybe like one you've seen in the past. It basically is showing us a router in the middle and 3 groups of PCs. And we notice there's this little blue cloud, which this textbook likes to use. And there are these numbers next to the host. These numbers are the IP addresses, the kind like you are assigned on your machine when you need to get something done. So we see that this network's been broken into 3 parts, and we notice something interesting. All of the addresses in each one of these things kind of start with the same range. These all start with 223.1.1, and these start with .1.2, and these start with .1.3. The manager, the administrator of these IP addresses has chosen to subnet their network. And for historical reasons, it's been the case that we have chosen to break this number up into 4 8-bit numbers and write them down as a set of 4 base 256 numbers, where each one of the 4 numbers in an IP address can have the value from 0 to 255. So if you get to 0 to 255 and you're at 255 here and you need to add 1 more to it, this is going to go back to 0 and you're going to add 1 to the next one. Just like in base 10, if you get to 9 and you add 1, you put a 1 in the next column and convert back to 0 again. So base 256 is a little bit tricky, and we have a couple of things that will probably help you. There's a couple of tools available, and I'll try and share some details on a couple of those things here. And I think I have some of them uploaded here for you. I'm going to take a quick peek and see if I have those handy. I thought I'd open those up, but maybe not. I may have to grab those a little bit later for you guys. Maybe I'll remember and go backwards in time and do it in the first lecture. Okay. So how are you going to actually manage this router? So this router has 3 subnets attached to it, and so this router belongs to 3 different networks. It belongs to this network and this one and this one. And because it belongs to 3 networks and has 3 physical interfaces, it needs 3 different IP addresses. So a router will have as many different IP addresses as it has physical interfaces. And it turns out we can get pretty good at not having to throw hardware at everything. And so you can actually have multiple logical subnets with different ranges of subnet numbers on the same physical interface. So what that means is not only will you have a different range of IP addresses, including one for the router on every interface, but sometimes you'll have more than one on the same interface. And we'll learn a little bit more about that a little bit later. Here's a switch. It's always written as a square here, and this is an Ethernet switch. And for our course, the switches are transparent, which means they're invisible. They do some things. It doesn't mean they're useless or passive, but it does mean that we're never going to see that our packets stopped along the way, that we see routing tables being built. We're not going to see our IP addresses change. We usually won't see anything happen at lower layers as well. But we will see the switch help us manage traffic. Okay, and then here's a Wi-Fi router on this LAN down here. And in each of these cases, the router is sort of managing the pool of addresses in each of these directions. All right, and so we'll talk a little bit more now about subnets. And they've drawn the pictures a little more carefully, almost perfectly this time. What they're showing is the subnet, this blue cloud, does include the port on the router that's providing them the service. And so they got it right here, and they kind of left a gap, but you kind of get the little better of an idea. And so this consists of subnets. So what is a subnet? It's taking an IP address and dividing it into other parts. There's one part of the address that is going to represent the network number that all addresses will share. There's another part of the address that will represent the host number, and so we're going to talk about that division and how that works. Maybe more relevant is to explain why we have subnets. We have subnets to allow us to define a boundary around a certain collection of computers who are to share certain information with each other and make it clear where traffic should stop. So for example, a lot of people think that naturally that you buy routers to connect networks together, and you do. But I will tell you, when you're trying to understand kind of how subnetting and how routing works, I found it much more helpful to think of routers the opposite way. I think it's helpful to consider that you put a router in to divide a network up, to split a network into pieces. And so these subnet ranges help us define which part is on which side of the router and which part is on another. In this example, we see there's been some numbers added to the ends of these addresses. And you remember how we noticed that all of these started with a certain same prefix? And we'll put a number after them these days to indicate how many of the bits are for the network number and how many are for the host number. And you remember I mentioned a slide or two ago that IP addresses are sort of divided into two. So every host has a full-blown 32-bit address, always, no exceptions. Whether it's private or public, inside or outside an institution, a small host or a giant server, with IP version 4, they all have 32 bits. And so burn that in. That's a constant that doesn't change with IPv4. What changes is the dividing line between the parts that are network and the parts that are host. And so we'll have some exercises to kind of help you learn more about it. The book has backed away somewhat in diving into the depths of subnetting, and I miss that actually, because I think mathematically there's a lot of elegance to it. You gain a lot of insight into how binary numbers kind of help make networks happen and the scale that we're dealing with on things. But I've got some tools that will help us kind of navigate through this a little bit more. So what this one basically is saying is that if I were to take 223.110 and I were to write it out as 4 base 256 numbers and then convert each of them to binary. So the 223 would maybe be 11101101, and then 1 would be 00000001, and the next one would be 2, and the last one would be 24, which is going to be 00001100. Then that's a set of 32 bits. I go to the 24th one, which is right here, and this part is my network number, the first 24 bits, and the last part is my host number. So that means all the devices on this LAN are all going to share the first 24 bits together. The only place where they're going to differ in the way you're going to give them independent addresses and tell them apart from each other, it's all going to happen in the last 8 bits. Okay, so how many subnets are on this network? Well, I can't tell by just looking at the number. I've got to have that slash notation, that extra part here. But what I can tell you by looking at the routers that are on here is what should be. There should be a subnet here, and here, and here. But there are 3 routers and they're connected together. And guess what? Every one of the links, even though there's only 2 devices on them, every one of these is a subnet as well. So I'm going to have to build 7 subnets, no 6 subnets. And with the old days, it used to be easy to figure out where the dividing line was between network number and host number. In fact, nobody ever needed to tell you where the dividing line was. You used the value of the first part of the address to kind of set that aside. That was one simplification that's gone. Another simplification that's gone is that these dividing lines between host and subnet always occurred at the dividing lines between the 4 base 256 numbers. So, well, that makes it easy. So it's either 1 base 256 number and then 3 more of network, or 2 base 256 numbers and 2 more of network, or 3 base 256 numbers represented the network and then 1 more of a host. So let me be a little more crisp here with the terminology because I don't want to mess this up. You have 4 base 256 numbers. This is always how we write them. It doesn't matter where the dividing line is. Even to this day, we still write them as a set of 4 base 256 numbers, as 4 8-bit numbers. When we had classful internet addressing where you could just take a glance at a number and immediately tell where the dividing line was, it's either here, here, or here. The network part was always on the left. The host part was always on the right. The only question was how much of it was net. Was it just 1 number? Was it 2 numbers, 3 numbers? And the same with host as well. That was very simple and efficient, but it was extremely wasteful of addresses because we ended up giving people big blocks of numbers that they didn't really need, and we ran out too fast. So we scrambled and did some recovery and decided that we needed to be a lot more fine-grained in how we handed addresses out. So if you are on a network that only needs 32 addresses, then you are only going to be given 5 bits of host address, because 2 to those 5 bits is the 32 addresses you need. And all the rest of it is going to be network number, or as this slide calls it, subnet part. What they've done here was somebody needed 512 addresses. I know that because I can see there's a division right here, and this is 9 bits. Now you notice this space? So these are the spaces between the collections of 8 bits, the base 256 numbers. Just because I divided up here in the middle of one of these doesn't mean I'm going to move where that space is. I'm still going to write this number out as this number in decimal dot this number dot this number dot this number to keep from going crazy, to make it easy on us. But I have to use this to say, the dividing line is on the 23rd position. It's after the 23rd bit. So this part's going to be my subnet part, and this part's going to be my host. So you just count however many bits there are here. In this case, there are 9, and you take 2 to the 9th, and you get 512. And so you're going to have 512 addresses here. How many of these networks could I have on the internet if this is the only way I did all of them? Well, you can calculate that. 32 total bits minus 9 for hosts for each network is going to give you 23. So 2 to the 23 different networks, each of which is 2 to the 9th in size, gets you to 2 to the 32. That's the way that works. Okay, so we'll look at some examples, but moving on to the question of how do you get one of these addresses? Well, there's kind of 2 meanings to that question. One of them is, who do you go to get one? Well, ultimately, you go to the Internet Assigned Numbers authority, and we'll get them from them, and they distribute them out to the regional network information centers, and you can get them assigned that way. But this one's asking a little bit of a different question. This is asking, how does it get assigned to your specific PC? In the old days, it was hard-coded, but these days we use a protocol called DHCP. And it's a program, it's defined in an RFC, of course, but it's a block of code that sits on your operating system. And when your PC first turns on in the morning, for the last 20 years, people have wanted to get onto an IP-based network so often that it's the default thing your operating system tries when you just turn it on. If it sees a network is out there, like the minute a Wi-Fi network is attached, it immediately sends out a DHCP request to get an IP address from a router. So the overview is basically you broadcast a discover message to see if there's anybody out there that can help you. You get one or more offers back. You choose one and say, okay, I choose you, Pikachu, and then you're going to get your IP address back. So that's typically something that's handled by the router. In this diagram, they show that you can run it on a separate server, but you never do. It's something that a router wants to do. It makes the router more useful to you, and router vendors want you to want your router, so they put this stuff in. So what you'll do is you'll hand the block of addresses, and this is a /24, so 24 bits are network and 8 bits are host. So it's going to be given a range of 2 to the 8th of these 32-bit addresses with every permutation of these 8 bits from 00000 up to 11111111, and it will hand them out. It may reserve a few. It will keep one for itself. 4 it looks like it kept. And the rest of them, when you turn your PC on, you're going to send a DHCP request over here, and it's going to give you back one of these addresses and make a little note that it's been assigned. So that happens automatically. So what this shows is a little bit of a detail in the client shows up on a network. It sends out a request. Is there somebody out there? A DHCP offer comes back. There's a transaction ID that's used to try to keep from being confused if more than one DHCP server responds to you. It makes an offer. It makes it good for a certain amount of time. And the client says, okay, thank you. I'll pick this address, and you'll send it back. Until you have an address, how do you send something on the network? I mean, how do you even issue this DHCP request when you don't even have an IP address? Because IP addresses are required to send information out on the network. Well, we use a trick. We use all zeros. So whenever you see a packet with all zeros on the network, it means that it's a DHCP broadcast almost certainly. And where do you send this thing to? Well, you're going to broadcast it to all devices on the LAN, all the IP subnet members. So you'll use a broadcast address for it. So at the IP layer, broadcast looks like this. And it's a 32-bit address as well. It's another IP address. It's all ones, but instead of writing 32 ones, we write 4 base 256 numbers. And here's what they are. And the same thing, if you need to send it out, it's going to come from all zeros, and we're going to write it as 4 base 256 numbers as well. So that's how you get your DHCP. Now, there's other things that you need to kind of get going. You need to know your router IP address, the default gateway it's called. You need to know the domain name you're supposed to use. You need to know some DNS server addresses and a variety of other things. And so DHCP has grown more sophisticated, and they now hand you all of this junk back at the same time. So here's a snapshot that's been reformatted from Wireshark, where you see that a device with this physical MAC address sends out a DHCP message. So it's going to come from all zeros, and it's going to go to everybody on the LAN. And you're trying to ask for an IP address, but you would also like your subnet mask, you would like your router, you would like a DNS server, you'd like to know the domain name. There's some other stuff that you may request in there. And the reply is going to come back, and they're going to basically give you an IP address, and they're going to tell you, here's the list of IP addresses you have to choose from. Usually you don't get a list to choose from. Usually you're told the one to use, but it supports the ability to do that. And if you do get a list, you pick one of them. Here's the name that I want you to use. Here's the subnet mask. Here's my IP address. Here's what type of message this is, and blah, 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 blah. All right? So that's the way it works. So the how do you decipher when you get one of these 32-bit addresses, sort of what's the network part and what's the subnet part? Well, here the ISP, here we're kind of asking the other question. The ISP has been given by the Internet Assigned Numbers Authority a block of IP addresses. And so they gave them a block of addresses, and the line on here is actually wrong. The line should stop right here, and I know that because of this number right here. So the ISP has been given a block of addresses. They've been told, look I'm going to give you some addresses. They're all going to start with the same 20 bits. And I told you that with this number right here. So they're all going to start with the same 20 bits. The remaining bits, however many there are, and by the way, there's 12, and I can either count these or I can say 32 bits minus the 20 leaves me with 12 left. The 12 bits, manage carefully because that's all you have. You're going to have to use these 12 bits, permutations of them, for all of your customers. And I know that your customers are going to want to not commingle your traffic with your other customers. So they're going to want routers at the edge of their network. And they're also going to want it to manage traffic over the telephone company network or the cable company network, et cetera. So you're going to have to do more than just kind of hand these out one by one. You're going to have to organize them into blocks. And so the ISP says, okay, I get it. How many customers am I going to have? Well, that kind of depends on how big they are. Well, let's say for this block of addresses, I want to go after decent-sized companies that maybe have, half a thousand devices, 500 devices, something like that. Okay, well, if you're telling me you need 500 devices, I can tell you that because log base 2 of that is something like 8 point something, you got to round up. You're going to need 9 bits to come up with enough permutations of those bits to give each of these customers 500 addresses. In fact, you're going to give them 9 bits, so they're going to have 512 addresses because that's what 2 to the 9th is. So you might as well start figuring out how many of these blocks of 9 bits can you give out. So if you're going to give each customer the ability to play around with the last 9 bits, and the first 20 bits are fixed, you don't get to change those, how many bits does that leave in the middle? Because that's how many times you can do this. Well, I have 20 coming off of 32, and that leaves me with 12. And now I'm going to hand 9 bits of those and give that to the control of the network manager. That leaves me with 3 bits left. So I have 3 bits in the middle between here and here, and they range from 0, 0, 0 all the way up to 1, 1, 1. There's 8 of them. That's it. You only have 8 customers. Each of them can have 512 addresses, and each of them is, of course, every address all the way up and down the line is always going to be 32 bits. But the way you're going to define which ones the organization here has is you're going to say, all right, the first 20 bits, we know what they are, and you're the first organization, so your next 3 bits are going to be 0, and the remaining 9 bits, I'm going to let you play with. So I'm going to give you everything for the last 9 bits from 0s to 1s. So your IP address block is going to look like 11111000, 000101111, 0001. That part was fixed. I'm going to give you 000 next, and then all zeros for the rest of the 9 bits. So you write that number down in binary, you divide it up into 8s, and you convert each of those 8s into a decimal number. And this is what you come up with. Well, that looks exactly like the one up above. What's different is the subnet mask. Well, let's do another one. Let's say we get down to the first organization in here. Their 3 bits in the middle are going to be 001. That changes the value of this 8-bit number. It is no longer 16. Now it's 18. 00010010 is 18. So this now turns into 18. It's still a /23, which means you get the last 9 bits, and you continue on from there. So the way these networks remain separated is one router is going to be responsible for this network number, and another router is going to be responsible for this one. And so at the ISP, they have 8 connections coming out with 8 high-speed lines going to 8 different customers, and these are the numbers they put on each of these separate router interfaces. If I can draw it here right. Okay? So you remember how I tell you there's 8 interfaces, so a router's got to have 8 subnets? Well, here they are. So that's the way that will look like. So things are very elegant. You can group these together. If somebody leaves, then it causes you a little bit of a problem. While all these are together, you can advertise to the world that I have this entire block of /20s. If somebody moves around, it's going to complicate things a little bit for you as well. So ICANN hands these numbers out. We need to spend a little bit of time on network address translation. One of the reasons why you don't all use IPv6 addresses all the time, which was designed to replace IPv4 because we were running out of addresses quickly, is because we figured out a way of sort of conserving things. Now, you remember my discussion about you go to the university, you pick up a phone and you dial 0. You're not going to get the same telephone company employee as if you go to a payphone and dial 0, or as if you go to an office building downtown and dial 0. There's numbers that are being reused, and the same thing happens on the internet as well. So what we did is we took 3 blocks of numbers out of commission. One of them was owned by the Advanced Research Projects Agency. They had a big block of numbers where the network part of the address was the first 8 bits, and the remaining 24 bits were host. So that meant the user, the owner of this network, had 000000110. That's not quite right. 1010. That's 10, and the remaining 24 bits, they got all those permutations for themselves. So that was 2 to the 24th, well over a million addresses, and they didn't have a million computers. So what we've done is we've banned this address, perfectly good range of addresses. We banned it from the public internet. It cannot be routed over the internet. If any router sees it, it will drop it and send perhaps an error message back, or maybe just drop it and tell you nothing. Why did we do that? Because we want every organization that would like a big block of addresses to be able to use this one. So I can use 10s, and in fact, if you are on campus and you look at your IP address, you have a 10 dot address. But if you go to a different university across town and get an address using DHCP and you see the address you've been given, you'll be given an IP address even if you're not allowed to access their servers and things. You have to get past the Wi-Fi password. But you'll be given an IP address, and it'll probably be 10 as well. If you go to Shell Oil downtown, you're going to have a 10 inside. So this is a big advantage because now the network manager has over 1 million addresses to play with. They can divide them up how they want, et cetera. The problem is they can never be seen on the internet. Well, then how am I going to get a packet out there? There's going to be a device in the middle that runs this program called network address translation, and it keeps track of a very small set of public IPs. Now, in the book, every example they use, they have a single public IP address that's been assigned to the router. In reality, that's not the way it works. In reality, you do have a pool of public addresses, just like DHCP has a pool of addresses to hand out to you. NAT's going to have a pool of public addresses to hand out. And what it's basically going to do is as you send a packet to the outside world, it will make note of the address that you have, and it will swap it out for a public one temporarily so that your packet can go on. It will come back to that same public address because the outside world has no idea that you have this address. They could never send anything to it. It's illegal on the internet. So they know you by this public address that you've been loaned for the moment, and it just has to, the net software has to undo this on the way back in. It has to convert this public address back into the private one that you were using. And if you need to share more than one user with the same address, well then obviously you're not going to be able to give them separate public addresses. If that happens, you need to find another way to keep them apart. And so what this NAT server does is they already know that everybody's going to be given the same public IP address. So what if 2 people need to go to the internet at the same time? Well, what if we keep track of a different port number for you? So we'll give you this address, but we're going to give you a port number, say 5000 for the first user, 5001 for the second user, 5002 for the third user, and so on. And I'll have to keep track of what port and IP address you really were coming from, and send the packet out, and when it comes back, swap it back for the real one again. So that's another way to do it. If I can't keep you separated by different public addresses, then maybe I'll keep you separated by the combination of one public address and different port numbers. That's okay. That works fine as long as they can keep track. So you're just going to use one IP address in the outside world. And again, like I said, that's not the case for any decent organization. In fact, the University of Houston has, I think the last time I looked, many tens of thousands of addresses. Tech de Monterey has 500,000 addresses. I have no idea why. Stanford University has tens of thousands of addresses, public addresses that they can hand out to devices. Some they want to hand out permanently because it's a public server, but most of them are used for these transient, temporary connections where people are going out to the internet and then coming back in. So it also gives you some other advantages. You can change ISPs without having to change all of your mapping. You can give big blocks of addresses out at one time. So if an organization like a department on campus continues to grow, you don't have to redo addressing again. So you can do some longer range planning. But it's got to replace the IP address. It's got to remember what it changed you to so that it can change it back when you come back in. So here's an example of a packet coming from this private IP address, this user right here, who was assigned source port 3345. He's trying to get to a public internet server, and I think it's a web server because he's trying to get to port 80. So this is already a public address. I use DNS or whatever. I figured out this host address. It sits out here on the internet somewhere. It has the address of 128.119, what it says here, and I'm trying to get to port 80. So there's nothing here that needs to be changed right now. So you arrive at this router and you're sending your packet through. You are going to make a note that this user was using that, and you're going to reassign them a different public address and port number to come from. It's only the source that changes, okay? The destination doesn't have to change. So you arrive at your server over here. They give you the response, whatever it was you were looking for. Maybe it was a web page or something. Where are they going to send it back to? Well, they're just going to reverse these two entries. That's all they're going to do. They're going to reverse them. So the request came from this place, so the answer needs to go back to that place. It came from this IP address, so it needs to go back to that IP address. It came from this port number, it needs to go back to that port number. Why would it be any more complicated than that? And I was trying to get to you at this port, so when you answer me, you use that. That's who you are. You're going to be coming now from that address, so I can tell that it's from you. It makes it back to the NAT, and the NAT server sees it matches this block, so it's going to change it back to this one. So the destination is the only thing that changes. There's nothing that needs to change about the source. The source was this server over here. You can't change anything about him. You don't own him. But you do own this router, and so you can force your users here to change things. So that's basically the way that works. It's a little controversial because it kind of masks what's going on, but it's fantastically secure because no one can ever ping you, let alone hack you, because you've got an address that they can't reach. So this is sort of the dilemma that we talked about with Skype. If I want to call you on Skype and you're sitting behind your institution and you have a 10 dot address, I could never reach you. So we're both going to have to go to an intermediate public server and establish our connections that way. Once you've opened a connection through one of these NAT servers or through a firewall out to a public server, now there's a connection open. As long as you initiate it, then you're fine. Data can go back and forth all day long, but it can never start here and go back to this device without some changes at the server because you have a private address. Okay, so here's an example now that we're going to show with DHCP being built into the router, why they do this later after the DHCP section Tell me and we'll both know. I have no idea. But all they're showing you here is it gets encapsulated, it gets sent out to everybody on the network, a DHCP server responds to it, sends the answer back, and you get your request back. Okay, so this is like very, you know, unexciting, very uneventful, because we've already been over encapsulation several times, and we've already explained DHCP. So what this does, however, in detail, is it shows you a little bit more about what's going on. So there's some other stuff going on with IP. As I mentioned, there's IPv6 that's out there. It's a larger address space number that was designed to try to help us keep from running out of addresses. It has enormously large addresses. It's not necessarily the case that we think there will be 2 to the 128 hosts out there. And by the way, that's more numbers than we think there are stars in the universe. So even I can't really conceive of that much, since it's countably infinite. I'm not sure how many cells are in all of the living creatures on Earth, but I think it's smaller than this number as well. So there's got to be more structure to this number, and in fact there is. And we divide this number up into things that show what region of the world you're in, what network you're on. So there's some geographic stuff. So all the IPv6s for, say, Latin America all start the same. So we can learn some things topologically that help us a lot with routing. Because one thing I certainly don't want to do is to have to keep track of 2 to the any number anywhere near this one as separate routes in my routing table. So other changes from IPv4, the checksum was removed to speed things up. So I'll just say I wish you well, IPv6. And we also have disallowed fragmentation. We think if you want to do fragmentation, it's a cost on the router. We were nervous about routers running out of resources. We underestimated the hardware industry again for like the millionth time, or I should probably say the 2 to the 24th time. And what you're supposed to do in IPv6 is use MTU discovery and sort of probe and send these repeated probes out, testing different packet sizes until you find one that makes it all the way through without being fragmented. Well, who's got time for that? Well, no one has patience for that. And so this backfired, I think, because what I see people doing all the time is they just never send anything other than the smallest legal packet. Okay, well, what was the point of that? All you did was push up the ratio of header to payload, and you've permanently taxed the entire internet that uses IPv6 more than you need to by guaranteeing that this ratio is higher than it should be, just because you didn't want to allow fragmentation. You also have some new ICMP messages that are out there. We use both on the internet, and so it presents this problem. What if you send an IPv4 packet out of your PC, it gets to the edge of your campus, and the connection they have to the next hop is IPv6. You just take the entire IPv4 payload, header, IP addresses, the payload with TCP inside, and inside of that with your HTTP message, that whole thing can be buried inside of an IPv6 header, or vice versa. If you have a test network on campus of IPv6 frames and you need to connect it to another university where there's another little IPv6 test network, you're going to use IPv4 in between you. You can put an IPv6 thing completely inside of one. So what they're basically showing here is your payload can be anything you want. It can be HTTP, it can be TCP, it can be another IPv6 datagram. That's okay. You can put whatever you want in your payload. So in this case, you'd have all that detail in there. So you've got your little test network at your 2 universities. The reality in between is IPv4. This type of process is called tunneling, and it's used all the time. If you start up VPN software on your computer, it tunnels all the way to the other end to a VPN concentrator at the other computer. If you use a Tor, it does the same thing. If you open up a HTTP secure socket connection between your browser, it's a tunnel between you and a TLS or SSL TLS server at the other end of the network. Right? So this is done all the time. Tunneling is a very useful general procedure. Okay, so IPv6 isn't very widely adopted, primarily because we found ways of not running out of IPv6 numbers. So I put some stuff in here. If you're curious, I'll throw it out here if you want to look at it on kind of how IPv6 has been doing. There's a couple of things that I want to mention to you. There's a couple of websites that I want to show you that'll be helpful to you in your homework. And one of them is, and they're both out in Homework 5's folder. They're sort of URL links. One of them is the set of converters. They're the best I found. And this one is binary to decimal. If you go down here, they'll have a decimal to binary. You also will find they have binary to every other type of converter in the world. BinaryHexConverter.com is the overall site. You'll find lots of other ones there as well. The other site I wanted to show you was three sites actually. I don't think I gave you all three links. I'm going to have to give you the, oh, I did. This one is a subnet calculator where you can type in an IP address and sort of calculate things from it. It shows you the parts of the network that are network numbers and the parts that are host, for example. So I can say I have this address here. I need 512 hosts per subnet, whatever it is. So there's a bunch of these out there. So this is just an example. There's a new elegant breed of them out there, which is graphical. And for this one, I can decide I want to divide a network up, and let's say I want to divide it up into a pair of .25s. So I can click and do that. This 25 I want to divide into 4 27s. So this helps you picture how you can divide networks up and get things out. And then you can crank out a table that sort of shows you all of the network addresses with the suffixes on them and all the broadcast addresses, etc. We'll talk about broadcasts more next time. All right, so that's a good stopping point. We made it through the material we needed to for today. Hope you guys have a great day. Talk to you soon.